Okay, hi guys, let's get started. I'm recording this video because we missed some a few classes because of my business trip. Uh, okay, so in this time, I will introduce about the SSD architecture simulators, and then also I will briefly introduce about the term project of this this course. Sorry about that. So. Okay, so I will introduce about the term project of the this course, and then in the term project, so you will be requested to use architectural simulators. Okay, so okay, let's get started. So I will briefly introduce some several uh, architect SSD or storage simulators. Okay, okay, so in the architecture field, for architecture research, so we frequently use simulators, right? And it is because actually the architecture research area includes the both software and hardware, and then usually the architecture research includes the software hardware interfaces. So, so in order to perform the architectural research, so we may modify the hardware architecture, but actually, so it's not easy, right? So, in order to modify the hardware architecture, so which means that we need to modify the hardware devices, and then it's not possible, right? So we cannot modify the hardware components such as CPUs and then processors, and then also the devices such as SSD, right? So so for our research, we need to use simulators, right? And then the simulators are software, and then this software emulates the behavior of target devices, right? So so in this course, we are learning about the SSDs, right? Then the SSDs are uh, the hardware devices, right? So for architectural research, we need to emulate this hardware behavior of the target SSD, right? And then which means that we can use simulators to analyze or to implement our ideas on this SSD architecture, right? So architectural simulators. So okay, use the okay. So we can emulate the operation of SSD, and then this emulation is implemented using software, right? So then why do you need to use the simulator? So as I mentioned, so actually we cannot modify the hardware devices. Also, uh, it's a cost effective, right? So because we can just modify the software part, the software simulators, right? And then also the another benefit of the simulator is that we can apply the different configurations of target devices using the simulators, right? And then it's in the hardware devices, it's not possible, right? So actually, for the SSD devices, so we can just change for example, the bandwidth of SSD interfaces. Also, we can change the internal bandwidth of SSD. So we can change the number of flash devices, and then also we can change the clock frequency of the SSD processors. So actually using there's some software configurations of our target software simulators, so we can modify some configurations of the target devices, right? And then okay, for the SSD area, so there we can just have there are the two different types of the SSD simulators, right? The first one is the trace type. trace type simulators, and then the second one is the full system simulators. Okay, so what is the trace type simulators, right? The the SSD is the storage, right? And then actually, as I mentioned, the operating systems provides the SSD commands. So it just provides the SSD commands, right? Commands to the SSD. Then what is the response from SSDs, right? So as I mentioned, the basic SSD commands are read, write, and erase, right? It's a flush, right? So then, based on this read, write, and erase commands, the SSD performs the requested behavior, right? So, for example, in the NVMe, the operating system just generate the NVMe commands, right? And then the SSD just reads these NVMe commands and decodes the NVMe commands to generate the flash level commands, right? In order to access the flash devices, right? So we can just between the host system, so this is the host, and then this is the SSD. Then actually the operating system just generate the commands, right? So the trace type simulator means that we can just cut this part, and then we can collect this traces of the SSD commands, right? So we can just store so for example, by running some applications, then the operating system will generate some SSD commands such as read, write, and erase. Then we can store these SSD commands as as a file, and then using these commands, then we can just provide these commands to the SSD model, right? Then we can just check the behavior of the SSD using the distress type simulators, right? And then, so this is the some very basic memory or type storage architecture simulators, right? So we can just use some trace type, and then based on these collected traces, so we can just provide these traces to the trace type simulators, right? So what is the advantage of these trace type simulators? The advantage is that we can just implement only this SSD part, right? So, and then, so as I mentioned, I mentioned that the operating systems think that the SSDs are block-based device, right? Then, okay, actually the interface is very simple, right? So as I mentioned, so SSD interfaces are very simple, and then the SSD commands are also very simple. So we can just okay, actually we can just provide these simple commands to the SSD model. Then we can just check the behavior of the SSD. But so this is so because we can just focus on the behavior of SSD, then this trace type simulators just implement this SSD part, right? So it's lightweight. It's a lightweight, right? Lightweight because we just implement this SSD storage part, so it can be very fast. So we don't need to think about the behavior of the software, right? Software part is here, and then actually this software does not working. It it does not really working in this part. We can just collect some traces from the software. But so in this type of the simulators, so the simulator also includes the disadvantages. So what are disadvantages of these trace type simulators? the disadvantages of these trace type simulators are, so actually we cannot implement the interaction between the storage and host system, right? What does that mean? So actually the software, so for example, the read commands, software just requests the read commands, provides the read commands to the storage in order to, read some data from storages, right? And then by fetching this data, then software just run some the code that makes use of some fetched data, right? Then it will take time, right? Then also if some codes are executed, then another commands will be created by this software. So it's actually the host's applications interact with the storage devices, but using the actually this trace type simulators cannot interact with this storage simulators, right? Just we can just capture the traces and then just traces are given to the storage, right? So we can just implement the full system simulators. So then what is the full system simulator? Full system simulator also implements this host part, right? Uh, so actually the CPU is included, and then using this CPU model, then the full system simulators can run the host workload, and then also the operating system and then NVMe drivers can be implemented on this full system simulators, right? And then it can interact. So commands are given to the SSD part, and then the SSD interact to the response to these provided commands. So using the full system simulators, well, we can just investigate the interaction between the host side workload and then the SSD behavior, right? So first system operations are emulated in the full system simulators, right? As I mentioned, the processors, operating systems, and drivers can be implemented. It's emulated, right? Because this is software, right? So simulation result can be more accurate, but what's the problem? Problem is it's very slow, very slow, right? So it's because we need to emulate the host part behavior. So for example, the software execution and then the operating system. So the operating systems are very heavy, right? So these operations need to be emulated in the full system simulators. So it can be very accurate, but it's very slow. So this is the advantage of the full system simulators, right? Okay, so I will introduce about some several simulators, right? And then actually these simulators includes also the trace type simulators and then full system simulators, right? So okay, so and then actually I just selected some popular simulators, right? So when you read some the recent SSD research papers, then you can find that which simulators are used for verifying the author's ideas, right? So I also select some popular simulators. So also actually for the Tom project, that you can just select the one of the simulators, and then you can use these simulators to perform your Tom project. Okay, the first one is MQSim. Okay, so MQSim was published in FAST, right? And then so this is the title of the MQSim paper, a framework for enabling realistic studies of modern multi-queue SSD devices. So what does that mean? So actually the MQ of the MQ sim represent multi-queue. Okay, so multi-queue SSD devices. Okay, so this slide shows the some internal components of a modern SSD. Okay, so so as you can see, the modern SSD includes the somewhat complex architecture, right? So as I mentioned, the SSDs are also the some independent systems, and then these independent systems include the embedded processors, and then also the firmware, the software, the system software, and then also it includes the DRAM and then the flash memories, right? It's a storage, right? So we can just understand the some internal the architecture of the this as modern SSD like this. It's a front end part and then back end part. So what is the front end part? The front end part includes the some software part and then the host interfaces, right? So and then the back end part just implements the flash interfaces, right? So based on the host side commands, these host side commands are decoded into the flash level commands, right? The flash interface command, right? And then these commands are given to the flash memory, right? So this is the backend part. And then so the SSD also includes the front end part. Okay, so backend part, so we can actually use some different types of NAND flash memory, right? Actually, so uh, we can use some different types of the memories, such as the modern the the modern non-volatile memories such as PCM and then the MRAM or 3D exploit. But the 3D exploit memory is deprecated, right? So the backend is okay. So because the firmware will generate so actually the front end part will generate the flash level commands and then these flash level commands will be provided to the backend part. So we can just use some conventional the flash interfaces such as ONFI, right? Okay, so this part can be just implemented like some memory devices, right? So so the host CPU interact with like processors interact with the memory devices, right? So and then based on some memory device protocols, right? So, and then based on some conventional the the flash memory protocols, then the backend part can be implemented. So backend part, and then front end part. Front end part includes the host interface logic, as it's called the HIL in this paper. So it just implements some host side protocol such as SATA or NVMe, right? And then also the SSD includes the flash translation layer. So that's what we learned in this course. And then also it generates the flash commands. And then these commands are created by the flash channel controllers, right? So actually the NQSIM implements this backend part and then also the front end part. And then the MQSIM is the trace type simulators, right? So which means so we can just provide the commands from the host side, and then the MQSIM will receive this command, and then MQSIM will simulate the behavior of SSD, the modern SSD. Okay. Okay, so this is the some FTL part, and then FTL parts some. So actually, the basic FTL parts are just implemented inside of the MQSIM. Okay, so actually those are what we learned in this course, right? So the in-place write is not supported, so MQSIM also needs to support this part, and then the logical to physical mapping. So this is the flash translation. So this is to be also implemented, and then the garbage collection. The garbage collection is also implemented in the FTL. Okay, and then I mentioned that the MQ of MQSIM represent multi-queue. So why? What is different, right? Okay, so actually the MQSIM is developed for reflecting the behavior of NVMe. So NVMe, actually, if you read some NVMe documents, then you can find that NVMe implements the multiple command queue, and then these command queues are multiple command queues are managed. The managed, and then actually the SSD just selects some command from these multiple queues. Okay, so but in the conventional host interface like SATA, just implement the only one queue, and then this one queue is just uh, mapped to some core. There is a core, the core of the CPU. So but the CPUs includes the multiple cores. And then these command queues are just mapped to each core of the CPU, right? And the operating system just schedule this IO scheduler, right? And then actually this is some command queue from the process 1 and command queue from the process 2 and then command queue from the processor 3. And then it received some commands from some queues, and then actually there is only one dispatch queue, right? Okay, so IO scheduler, the IO scheduler of the OS part just select some command from the multiple queues from the multiple cores, right? And then actually these commands are given to the SSD devices. So this is some conventional uh, the queue model of the SATA, right? But the modern SSD includes the different queuing models, right? So so actually the multiple processors to generate the NVMe commands, right? The storage command, and these storage commands are given to the some IO request queue from the host side, and then these commands are collected by SSD devices, right? And then inside of the SSD devices, then there are multiple queues, like as I mentioned, there are the multiple command queues, the submission queues, and then completion queues. And then the SSD just manages these queues and then schedule some command from these multiple submission queues, right? So the modern NVMe SSDs are designed for parallelism, okay, right? So it is because NVMe, so actually the modern SSDs includes the multiple submission and completion queues, and then these multi-queue models is to be implemented for reflecting the behavior of SSD. So MQSIM just implements this one. And then also, so this is some another challenges of the conventional SSD simulator. So actually this paper just introduces that uh, the, the the disadvantage of the conventional simulator is that it's hard to it's hard to provide the steady state model. So what does that mean? So initially, the SSDs are empty, right? So which means the flash memories are all initialized, and then which means that actually the flash memories do not include the valid pages, right? But in order to perform the behavior of garbage collection, then we need to fill the flash memories using valid pages, right? And then actually it's called the steady state, right? So we need to write some valid data to the storage in order to uh, investigate some behavior of steady state model of SSD. But for write, such very slow, right? So actually, but the authors presented that MQSIM supports this steady state model, and then so which means that we can quickly simulate some steady state of the SSD. So and then actually they mentioned that MQSIM just implements some complete model of the request latency, right? So they mentioned that only this part, the conventional simulator just includes implement this part, but MQSIM actually, as I mentioned in the first part of the MQSIM, the MQSIM implements some complex internal architecture of the modern SSD. So and then the MQSIM just implements the timing model like this one. So some from user application to the host memory, and then host memory to the interface to the firmware, and then blah blah blah. So these parts are also implemented in MQSIM, right? So that's why the actually for modern SSD research, I believe the MQSIM is widely used. So because the MQSIM just reflects the behavior of modern SSDs, right? So, so the authors presented that the MQSIM can reflect the behaviors of conventional SATA-based SSDs and then modern multi-queue, so which means NVMe SSDs, right? So it just supports the multi-queue protocols, and then so it can just implement this uh, behavior, okay? The behavior of the NVMe SSDs, right? And then, so they also mentioned that the MQSIM can be integrated with the Gen 5 voice system simulator, okay? And then also this non-volatile memory part, right? The backend part. So this non-volatile memory part can be also implemented. Okay, so which means that we can configure some different types of number of memories for this backend part of the SSD. Okay. Okay, so you can check some source code of the NQSIM in this GitHub link. Okay, and then actually they also exhibit the accuracy of the MQSIM, right? So it's like the error rate. So this is some very old simulators, right? And then actually they also reported some accuracy of this MQSIM, right? So, so this is the simulator paper. So actually the simulator needs to reflect some real behavior of the hardware devices, right? So which means simulator papers also need some accuracy information. So which means how the simulators can how can simulators reflect how simulators can reflect some real behavior of other devices. So if you see this table, you can find that the error rate of this MQSIM, MQSIM is relatively low compared to the old SSD simulators, right? And then also compares the other simulators, right? Like this. Okay, so the conclusion. So SSDs, actually, the modern SSDs includes the very complex architecture, and then so also the modern SSDs includes the multi-queue model, like the NVMe protocols. So MQSIM just implement reflect the behavior of the modern SSDs, right? And then so they mentioned that the MQSIM is accurate, more accurate than the old SSD simulators, right? Also, it's open source, so and then you can download the MQSIM. Then you can also run some traces with the MQSIM. Okay, and then also you can find some lecture videos for MQSIM. Okay, so here also you can just search the MQSIM in the YouTube. Okay. Okay, so another SSD simulator is Simple SSD. So Simple SSD is called the Amber. Okay, and then this Simple SSD paper was published at Micro. Okay, so actually this is the Simple SSD 2.0. It's some newer version of the Simple SSD, and then as you can see in this in the paper's title, that you can find that this is the full system simulation. Okay, full system SSD simulator model. Okay, okay, let's see. Okay, so as I mentioned in the previous class, not in the previous class, as I mentioned in the previous slides, so actually the full system simulators are more accurate, right? Because the SSD needs to interact with the software working on the host side. But the problem is it's slow, right? It's slow, but we may also require some full system model, and then actually the simple SSD is the full system model that integrates the Gen 5 with some NAND flash simulators, like SSD simulators, right? Okay, so as I mentioned in the for the trace simulators, so this is some example of the trace file, right? So as you can see, the trace file includes some timestamp, and then process ID, and then also it includes some uh, the storage commands, right? So, but as I mentioned, this trace type simulators cannot implement the interaction between the software and the storage devices, right? That's the problem, right? So, so the authors also mentioned at this point, right? The relay system, the interact with the software. So software interact with some real SSD, but trace-based simulation. So we just provide the trace IO files. Then the trace IO file includes some storage commands, and then only this part, the storage commands are just provided to the SSD model, SSD simulator. Then we can just measure the performance of the SSD, but we cannot measure the interactive behavior of the host side behavior, right? So simple SSD. So this is some uh, architecture, like so the structure of the simple SSD. So simple SSD just offers full system simulation, right? And then the simple SSD was includes because the simple SSD is the full system simulators. Simple SSD includes the host part, host system part. So this is the host system part, and then this is the SSD part, right? So the host part just implement the functional CPU, right? So it's a very simple CPU model, and then using this simple model, then we can just run the operating systems, and then also we can run the some software, right? Some applications that run on this host system. And then, the simple SSD just to uses the Gen 5. Gen 5 is the, the full system model. So which means that we can also configure the, the parameters of these host systems, right? Because using the Gen 5, so we can configure the host system parameters such as the CPU frequency and then CPU model, and then DRAM performance, and then something like that. So we can adjust the performance and the configurations of the host system. And then also the simple SSD implements the SSD part, right? Then this host system is connected to the SSD using some SSD interfaces. And then like the MQ theme, the simple SSD also includes the host interface layer, and then the FTL, and then flash interface layer. And then so ICL is the sub translation, right? So this is the interface between the host interface and the FTL, right? So SSD, no, simple SSD also implements some detailed model of this SSD, right? And then also the simple SSD also implements some performance model of the SSD processor, right? And then so we can also configure these performance models of the SSD processors. Okay. So this is the feature. The author just mentioned that this is the some feature of the simple SSD. It accuracy. We can provide some more accurate so the interface the interaction model between the host and the SSD. Okay. So inside of so this is slide shows some internal architecture of the SSD model. Okay. So they just simple SSD some just classifies some SSD architecture as the computation complexity complex and then storage complex. So storage complex model is it's a NAND flash model, right? So also they just integrate their NAND flash simulator in the simple SSD. So and then they just implement this NAND flash model, right? NAND flash timing model. And then computation complex part. So as I mentioned, the simple SSD just implements the CPU, cache, and DRAM modules. So as I mentioned, so SSD also includes the internal caches because this is the embedded processors, right? And then also it includes the DRAM, right? And then inside of the DRAM, so we can just manage the page tables, and then also we can manage the buffers, right? So this part this part is also implemented in the simple SSD. The storage complex, as I mentioned, storage complex just implements the behavior of the flash memory, right? Then for the storage interface, so simple SSD supports some hardware-driven the storage interfaces such as SATA and UFS. So this is some generation, the older generation, the storage interfaces, and then also in, the it supports the NVMe and then open channel SSD, right? So it implements the NVMe protocol, and then open channel SSD means that some FTL functions are just implemented inside of the CPU, host CPU, right? So, the host, so, FTL is the part of firmware. So it means it's a system software. So, but open channel in the open channel SSD, these FTF functions are run by host CPUs, right? So some FTF functions like host-based FTL also is implemented. Also, like the NVM, so it's also implemented. It's an open channel SSD. And then so simple SSD also implements this device controller and then open channel SSD subsystem. So in the open channel SSD, so the CPU just provides the physical page address, right? So the FTF parts are just managed inside of the host CPU. So simple SSD, because the simple SSD is the full system simulators, and then it just implements the host system part, and then SSD part. So it can just implement the open channel SSD. Okay. So the authors also compare the simple SSD with the other simulators, right? So it also includes the MQSIM, right? Okay. So the Ember is the simple SSD 2.0. Okay. So conclusion is a Gen 5 integrated simple SSD 2.0. This is the full system simulator, and then it can reflect the interaction between the host software and the SSD, right? So this is the some also the simulator paper. So it also uh, analyzed the accuracy of this simulator. Okay. So again, also compare some MQSIM and then simple SSD 2.0. It's Ember. Okay. So MQSIM just focuses on some internal models of the SSD, but simple SSD 2.0, Ember, just focuses on some system interaction, right? Because it implements the full system model, and then it implements some detailed SSD model, right? So speed, the MQSIM is relatively fast. It is because we can use some trace files. But the authors also mentioned that we can just integrate the MQSIM with the Gen 5, right? So that means the full system simulation can be also possible with the MQSIM. But anyway, the simple SSD 2.0, we need to use the operating system. so it can be very slow, right? So we can select some simulators based on our purpose, right? So if we want to see if we want to focus on some internal performance and then internal behavior of the SSD, then we can use MQSIM. Or if we want check some interaction between the host system and SSD, then we can use the simple SSD, right? Okay, so I briefly explain about some two SSD simulators, right? MQSIM and simple SSD, and then now I will introduce about the FEMU. So FEMU is actually emulator, right? So what does that mean? So MQSIM is called the simulator, and also the simple SSD is called the simulator, but FEMU is the emulator. So actually the FEMU is based on the QEMU. Oh, no, QEMU. right? So QEMU is the virtualization tool, okay? So like the VirtualBox and virtualization tool. So like the VirtualBox and VMware, the QEMU is the virtualization tool. And then, the FEMU is implemented on QEMU, right? So actually, the FEMU just emulate the behavior of storage device the inside of the virtual machine, right? So so it means that actually the on the QEMU virtual machine, the SSD part is just replaced, and actually the FEMU just implement the behavior of SSD using the memory space. So which means the host RAM. Okay. So so this is so actually so which means the using the host machine that we can just run any applications, right? And then only this SSD part is just implemented using the simple model. And then actually the storage part is just implemented inside of the RAM. Okay. So this is the FEMU, right? So FEMU is also published at FAST 18, right? So this is the title of the FEMU paper. The case of a FEMU, chip accurate, state scalable, and extensible flash emulator. Okay, so this is the emulator. So then, what is the benefit of a FEMU? So simulator is simple and time saving, but it's a trace driven. So, like the MQSim is the trace based simulator, and then it can be very slow. Okay. So, and then it's not easy. It's not easy to learn some real software on this simulator because we can just collect the traces from the host system, and then only these host system, the traces are provided to the simulator. Also, we can use the hardware platforms, the real hardware platforms, right? But so as I mentioned, this is not easy, and then it's expensive, right? So using this hardware platform, we can implement the real software, and then we can run real operating system. But problem is that it's expensive and then it's hard to modify, right? So FEMU is the emulator, right? It is implemented on the QEMU, and then we can run the guest OS. So because this is the virtual machine. So on the QEMU, so we can run the guest operating system, like the host operating system, and then so we can run the real application, and then so these real applications will generate the storage commands, right? But the FEMU emulates these storage devices using host DRAM, so it captures the the SSD commands, like a storage command from the guest operating system, and then it just emulates the behavior of the storage, right? So it can be used for full stack research. Then it's cheap because it's just a virtual machine, right? And then so the problem is accuracy. Accuracy can be very low because we cannot implement the real the performance model of the storage processors. So uh, actually the storage devices are implemented using the DRAM, the host DRAM. So a FEMU can only so implement some latency model of the flash memory, right? So it's a FAMU, okay? So this is the accuracy range of the FAMU, and then you can also download the FAMU from GitHub, right? It's a QEMU-based flash emulator, and then also the authors mentioned that it's a scalable, so we can just implement some multiple channels, and then it implements the FTL, like the page translation, right? The logical to physical page translation. So this is the some payment model. So, so compared to the other the previous two simulators, the payment model is a relatively simple. So it is because it's just a virtualization tool, right? It is implemented on the virtualization tool. So and then it replaced just this storage interface, right? So on the guest operating system, on the virtual machine, on the guest operating system, then we can run application, and then it will generate the storage command, and then FAMU just to implement that TL, right? And then it just capture the storage interface. Then it can it can just emulate the behavior of the SSD, right? So you can interact with the also SSD, but this model is the very simple model, right? It is just the memory, okay? It is implemented to the memory of the host system, okay? So this is the FAMU. So you can also find the many papers that utilize that exploits the FAMU, right? So can be a good tool, right? But another some concern of the FAMU is the accuracy. Okay, so then another another simulator is the NVMe Bird. So this is NVMe Bird was presented at Fest 23. So it's a relatively the modern emulator. So you know the paper title of the NVMe Bird is the versatile software defined virtual virtual NVMe device. So it's a versatile, right? So so differences between the FAMU and NVMe Bird is that the FAMU just exploits the virtual machine, right? The virtual platform, the virtual machine that runs on virtual machine platform, right? But the NVMe Board is implemented on the Linux kernel, right? So NVMe Board is implemented as the Linux kernel module, right? So it can it's a the in the venue is it works on the virtual machine. So which means that the performance model of venue can be less accurate, right? But the NVMe board is just implemented as the Linux kernel module. So the Linux kernel directly interact with some NVMe board, right? So which means that the performance model can be more accurate, right? And also, the virtual machine model just includes some noisy part because it just run on the toaster system, and then it just includes some additional some virtualization layer, right? So and then this virtualization layer can work as some noise. But ambient word just directly works with the Linux kernel module, Linux kernel. So actually we can reduce this noise component. So NVMe board just implement some fake PCI interface and then fake devices like NVMe devices, and then it includes the native driver, then DRAM backend. Okay. So in the NVMe board paper, the authors also mentioned some driver level approach, and then so this is some old emulation approaches, right? So and then also they also mentioned the virtualization based approaches like FEMU, right? So they also mentioned the limitations of this virtualization based approach. But NVMe board, as I mentioned, the NVMe board just works like some Linux kernel module, and then say it can directly control manages the NVMe devices. So they mentioned that uh, the NVMe board can uh, reduce some noise part, noises, right? And then also he also mentioned that the NVMe board can support the conventional SSD, NVMe, and then some different NVMe based SSD, GNS SSD, and key value SSDs, right? So some recent papers also utilize some NVMe board. So if you read some SSD papers, several SSD papers also use this NVMe board. Okay. So, and then another part of the paper just implement explains how the NVMe board can reflect the real SSD behavior. So it just explains some configuration step. Okay, like when the SSD the system is booted. Okay, and then and also it explains some IO request. Right. And then the NVMe boards with the NVMe board we can just change some this backend part, but this backend part just represent present some different type of SSDs, right? Because NVMe board is the emulators, and then it just works as some kernel module, okay, on the host device. And then we can just change some device models like the conventional SSD or GNS SSD or key value SSDs. Right? So higher request is it can also work like some normal IO request. Okay. Okay, so emulation IO request and then performance model. So NVMe port also models the behavior of PCI link, and then the write buffer, and then the multiple the SSD devices, right? Like just using the multiple FTA instances, and then also it implements it emulates the behavior of some multiple channels and the multiple dies. Okay, and then they also compare the performance, right? They compares the performance of NVMe board using the real devices. Okay, then so the performance accuracy is like this. So you can also download the NVMe board code from the GitHub, right? And then they advertise that these interfaces and then the different types of SSDs are also implemented in the NVMe board. Okay. Okay, so another platform is the Cosmos Plus OpenSSD. So this is the real SSD development board, right? So it's a real hardware. Right? So until this part, so actually I introduced some SSD simulators and then SSD emulators, right? But you know, this OpenSSD is the real hardware, okay? And then this is the the photo of the SSD board, okay? So if you see that this OpenSSD board, you can find the FPGA part, right? Is the OpenSSD includes F- the Zinc 7000 FPGA SoC. So and then in this app and in this SoC, the the Zinc 7000 includes the ARM embedded processors and an FPGA part. So we can modify this FPGA part, but actually on the OpenSSD, FPGA part includes the host interface and flash interfaces, right? So already some programmable logic is occupied by host interface and then flash interface, right? So you can find some these flash memory DIMMs, right? So if you can get some this DIMM module, the flash memory DIMM module, then we can attach these flash memory DIMM modules on the SSD. But these flash memory modules need to be supported by the firmware, the existing firmware of the OpenSSD, right? So this is the real hardware, so which means that we can just modify the firmware, and then also we can just implement the host system. So, this photo just shows some real uh, the system configuration using the uh, OpenSSD, right? So you can find the OpenSSD board, and then this is the host machine, okay? And then the OpenSSD is connected to the host machine using the external PCI bus, okay? So it's a real SSD. So actually we can just modify the firmware of the OpenSSD, and then also we can, if possible, we can modify the programmable logic, the PI part of the FPGA, and then we can implement some of our ideas using the OpenSSD. So this is the real hardware platform. Okay, so now, so I quickly introduce about some SSD simulators, and then I also introduced the the OpenSSD, the real hardware platform. So now, I will briefly explain about some term project of this course. Okay. So theme of the term project is exploring SSD architecture. Okay. So actually, even though we have learned about some architecture of the SSD, it's not easy to modify some detailed architecture of the SSD. So that's why I set the goal of this term project as exploring SSD architecture. So which means that we can just change the parameters or configurations of simulators or emulators, and then we can just check some performance or some behaviors of SSD based on these changed configurations, right? So, as I mentioned, the theme of the term project is exploring SSD architectures. And then you can organize the team as the 1 and 2 members per team. Okay. Your team can include the 1 member, or your team can include the 2 members, right? But if your team includes the more members, then I expect the, the output from this team can uh, richer than the output of the single member team. Okay. You can use the following SSD simulators or emulators such as MQSim, Simple SSD, and VMU and VMUBird. Okay. And then you may collect some performance metrics such as the I/O statistics, like I/O performance, and then power and energy consumption, and then some instruction statistics, and then FTL statistics. Okay. So you need to also investigate the target simulators, right? So which means then you need to figure out which performance metrics can be investigated using the simulators. Okay. The project, you can just configure the simulators. Okay. Okay, and then you can use some workload such as the FIU and FileBench. So these are the real application that run on the real machine. Okay, and then for traces, you can just check some traces for the open source traces. So these are, you can check these pages for trace files. Okay, and then you need to investigate some performance result by some different design species, right? So in the project schedule, and then by the November 28th, you need to submit the proposal, the project proposal. The one page proposal is okay. So you need to include some SSD simulator, and then traces, and then also your LAN, your some project members in this project proposal. And then on the last day of this course, you will make a presentation. And then also you need to submit the project report. So for the presentation, I expect that each presentation will take the 5 to 6 minutes length. So which means that you also need to submit the presentation slide. And then also you need to submit the project report. And then the report length can be 2 to 4 pages. Then you need to present and write in English. So this course is the English course. So to practice your English, right? Because I believe so. Usually you want submit a paper in the international conferences, right? Then you can practice English, right? Okay, so this is the end of this lecture, and then good luck for your project, and then please, okay, and then also good luck for your exams, okay. Okay, thank you for your attention, and then see you later. Bye.